To MyProjectBazaar.com. Now we discuss about the product for design of adiabatic dynamic differential logic for DPA-resistant secure integrated circuits. Next we see the abstract for the product. The demand for implementing ultra-low power digital system in many modern applications such as mobile systems, sensor networks and implant biomedical systems has increased the importance of designing logic circuit in sub-threshold region. These emerging applications have low energy as the primary concern instead of performance, with eventual goal of harvesting energy from the environment. In sub-threshold logic, the circuit operates with the supply voltage VDD lower than transistor threshold voltage VT and utilize the sub-threshold leakage current as the operating current. Conventional CMOS logic circuits utilize the sub-threshold transistor can typically operate with a very low power consumption and it's gradually depend upon the supply voltage as CLLF VDDs. Recently, adiabatic logic style has emerged the promising approach of strong inversion region to reduce the dynamic power consumption significantly without sacrificing noise immunity and driving ability. These circuits achieving ultra low energy consumption by steering currents across device with a low voltage difference by the gradually recycling the energy stored in the capacitive loads. Behavior of adiabatic logic circuit in weak inversion or sub-threshold region is analyzed in the depth first time in the literature to create improvement in ultra-low power circuit design. This novel approach is efficacious in low speed operations where power consumption and longly are the pivotal concern instead of performance. The schematic and layout of a 4-bit Carluga head adder has been implemented to show the workability of proposed logic. A 4-bit Carluga head adder unit is adapted as a reference circuit. Analyze the energy dissipation along the sensitivity of energy dissipation on supply voltage and temperature variation also discussed in our process. Next we see the flow diagram for the product. The first we focus for the CMOS design based SAL method. This method to reduce the dynamic power consumption for overall CMOS architecture. We implement the 4-bit Carluga head adder architecture for overall CMOS functions. This function to improve the Carluga addition function for our SAL based methodology. SAL method successive adiabatic logic method to improve the logical implementation for 4-bit Carluga head adder logic, because previous conventional Carluga head adder logic to increase the number of CMOS transistor count and to improve the overall area and power, all the things. But this kind of 4-bit Carluga head adder to reduce the overall function based on the sub-threshold adiabatic logic. See sub-threshold adiabatic function to reduce to the fixed input voltage level and to improve the addition performance level and to increase the performance analysis for power and area and speed complexity for overall performance. This function to improve the CMOS overall 4-bit Carluga adder structure. This function every architecture to implement based on the PMOS and NMOS combination. This combination of transistor to improve the overall performance level. We use the 0.25 micrometer library for overall CMOS addition process. This addition process to reduce the carry propagation time and to improve the addition processing speed level for overall architecture time and to reduce the leakage and dynamic power consumption for our overall architecture based on the SAL logic function. This is the final flow diagram for the process. Finally, we see the output for the product. This is the sub-threshold based adiabatic logic CMOS design. This design to focus the overall addition process for overall architecture. This is the final design. This design to implement the half adder and full adder based 4-bit Carluga head adder logic. This adder to implement the basic XOR gate and the XOR gate adiabatic logic and AND gate adiabatic logic and OR gate adiabatic logic to be present and NOT gate adiabatic logic. These 4 kind of gates to be present in our required Adiabatic logic based 4-bit carrier adder architecture designs. This design mainly based on the CMOS based logic. CMOS means PMOS and NMOS combination of transistor to develop the physical oriented architecture process and to simulate the required input voltage to be passing in the our carrier head adder architecture and output to be getting to the final 4-bit carrier addition process. 4 sum output to be generated and 1 carry passing to the next addition process and to finalize the carry out to be presented. So totally 5 bits to get it to the output data bits for our overall architecture function. These are the final output for our overall simulation architecture process. Then we go to the running process. This running process to create the T-Spice and the W-edit waveform for our overall architecture process. T-Spice is the background running process for overall architecture functions, and the W-edit waveform for given input voltage to be performed for the overall addition process, and to sum 0 to sum 7 and the final carry out to be passed. Any one of the sample A input, B input and C output voltage level to be passing. If the voltage to be A0, 1, 0, 1, 1 and the sum values to be initially sum 1 is equal to 1, the carry values to be C1 to be passing to the output function. So every time to passing the same section to be passing in the each and every architecture based process. These are the final simulation diagrammatic representation for our overall architecture functions. This is the final timing diagram output for required input voltage based on the output voltage representation for 4-bit carrier head adder architecture process.